Evaluating linear functions. An equation in two variables is called a function if for each input we get exactly one output. In example 1, we're given an equation y equals negative 4x minus 4. And we're asked to determine the value of y for different values of x. So in this example, the x represents the input and the y represents the output. So let's begin with x equals negative 9 as our input. What this means is that we go to our equation, and where there's an x, we replace that x with our input, which in this case is a negative 9. Leaving everything else in the equation as it is. Then we perform the order of operations to compute. So negative 4 times a negative 9 is a positive 36. And 36 minus 4 gives us 32. So notice one input resulted in exactly one output. Now let's repeat for x equal to negative 5. Again, we go to our function, our equation, y equals negative 4 times x, but this time our x is a negative 5 minus 4. And then we compute, so we have negative 4 times negative 5 is 20. 20 minus 4 gives us an output of 16. Repeating the process for x equal to 0, we have y equals negative 4 times 0 minus 4, resulting in 0 minus 4, because negative 4 times 0 is 0, and giving us a final output of negative 4. In our last example, x equals 3. Replacing the x in the equation by a 3, and then performing the computation, negative 4 times 3 gives us negative 12. Minus 4 results in a final output of negative 16. In example 2, our equation is not written in simplified form. You have a choice. You can go ahead and evaluate this equation for different values of x, leaving it in this form, or you can simplify first and then perform the computations. I recommend simplifying first so that you have less work to do when you are performing the computations. So simplifying our expression in our equation by distributing the 4 through the set of parentheses, we get negative 5x plus 24x plus 20. And combining like terms, we end up with 19x plus 20. So our equation can be written equivalently as y equals 19x plus 20. Now when x equals negative 9, we replace the x in the equation with a negative 9 and perform the computation. 19 times a negative 9 gives us a negative 171. Plus 20 gives us a final output of negative 151. Evaluating our equation when x equals negative 5, Again, we replace our x with a -5. And 19 times 5 is 95. So since this is a -5, we have -95 plus 20, giving us a final result of -75. When x equals 0, replacing our x in the equation with a 0, we end up getting 0 plus 20, or the output of 20. When x equals 3, we have y equals 19 times 3 plus 20, and 19 times 3 equals 57, plus our 20 gives us a final output of 77. Evaluating linear functions involving fractions. In this video, we look at equations in which we have fractions. The process of evaluating these equations at different values of x is the same, it's just that we are going to have to deal with fractions. So consider this first example. We are trying to evaluate the equation y equals 2 plus x over -4 at different values of x. So replacing the x in the equation with our given x value of -3 in our first row of our table, and then performing our computation using the order of operations, 2 plus -3 in the numerator must be done first, giving us a -1 over the -4 that appears in the denominator, resulting in a final output of positive 1/4. In our second row, we're evaluating this equation at x equal to -2. So replacing the x in the equation with a -2 and performing the computations, 2 plus -2 gives us 0, divided by a -4, which simplifies to 0. 0 divided by any non-zero number equals 0. Finally, let's evaluate this equation at 4. Replacing our x value in our equation with a 4 and performing the order of operations, 2 plus 4 gives us 6 in the numerator over -4. We see that this fraction can be written in simplified form by dividing the numerator and denominator by a common factor of 2 for a final output of -3/2. In example 2, our equation consists of two fractions being added together. This is not as simplified as our previous example, so it might be to our advantage to perform the simplification of adding the two fractions together before we go to evaluate at different values of x. So noticing that there is a common denominator of 18, we can multiply our numerator and denominator in our first fraction by 3, so that we have 3x over 18 plus a -3 over 18, which now allows us to add those two fractions together, getting a single numerator, 3x minus 3, over a single denominator of 18. Now evaluating this simplified version of our equation at -8, replacing our x with a -8 will be a little bit easier to compute. So performing the order of operations on the numerator, 3 times a -8 is a -24 minus 3 all over 18. Continuing the simplification process, we subtract -24 minus 3 to get -27 over 18. And then noticing that there is a common factor of 9, we can divide numerator and denominator by 9 in order to obtain the simplified fraction -3/2. Now let's evaluate our equation at 3. Replacing our x with a 3, and then simplifying our numerator. 3 times 3 is 9. 9 minus 3 is 6. We have 6/18, which simplifies to a single output of 1/3. Finally, let's evaluate this equation at 7. Again, replacing the x with a 7, then simplifying our numerator. We have 3 times 7, or 21, minus 3 over 18. 21 minus 3 is equal to 18, and 18 over 18 simplifies to 1. In example 3, our equation is y equals 5/6 times x plus 10. Our computations for different values of x will be simplified greatly if we can express this equation as a single fraction. So thinking of x as x over 1, and remembering how to multiply fractions, since 5/6 is being multiplied to the x over 1, we simply multiply our numerators, multiply our denominators to get 5x over 6 plus our 10. Thinking of 10 as 10 over 1, we see that we need a common denominator of 6 in order to be able to add these two terms together. So we multiply our numerator and denominator in our second term by 6 in order to get 5x over 6 plus 60 over 6. Now we have a common denominator, and we can add our numerators, 5x plus 60, and place that over a single denominator of 6. Now let's compute y for different values of x. When x equals -10, we replace the x with our -10 and perform the order of operations. 5 times a -10 is a -50 plus 60 over 6 is what we get after we perform the first operation. -50 plus 60 is 10 over 6, which can be simplified by dividing numerator and denominator by the common factor of 2, resulting in a final output of 5/3. Now evaluating our equation at -7, we replace our x with a -7, and performing the order of operations, we have 5 times a -7, which is -35, plus 60 over 6. Negative 35 plus 60 is 25 over 6. And since there are no common factors between 25 and 6, this fraction cannot be simplified further. One final computation. Let's evaluate our equation at 3. So we replace our x with a 3. Performing the order of operations, we have 5 times 3, which is 15, plus our 60, all over 6. 15 plus 60 is 75 over 6. And since there is a common factor of 3, we can divide the numerator and denominator by that common factor, resulting in a final output of 25 halves. Evaluating exponential expressions. We begin this video with a review of the definition of an exponent. The definition states that a base a raised to a power of m means that that base of a is being multiplied to itself m different times, which means that there are m factors of a being multiplied together. There are 2 properties of exponents that will be useful in this video. The first property says that if you have a base a raised to the 0 power, that will equal 1, unless a equals 0. If a equals 0, and you have 0 to the 0 power, that is not defined. If you tried to compute 0 to the 0 power on a calculator, it would give you an error. As an illustration, consider 4 to the 0 power. Since the base is a 4 and not 0, 4 to the 0 power, according to this first property, is equal to 1. Property 2 says that if you have a base a raised to a negative power, that you can rewrite this as 1 over that base of a raised to the positive power. The movement to the other side of the fraction is due to the negative exponent. Once you've moved that base to the other side of the fraction, the exponent becomes positive. As an illustration, consider 3 to the negative 2 power. The negative exponent means that that 3 can be moved to the other side of the fraction. The power becomes positive after making that movement to the other side of the fraction. Since 3 times 3 is 3 squared, this fraction can be simplified to be 1/9. We now consider equations in which there is an exponential expression. Consider example 1. We're asked to determine the value of y for given values of x, where y equals 2 to the x power. So just as before, when we're evaluating an equation at x, we replace the x in the equation by the numerical value we're given for x. Remembering our properties of exponents, the negative exponent tells us that this 2 needs to move to the other side of the fraction, and in doing so, the power becomes positive. Remembering that 2 cubed is 2 times 2 times 2, we get a simplified output of 1/8. Evaluating this equation when x equals 0 gives us 2 to the 0 power, and according to our properties of exponents, 2 to the 0 power is 1. Evaluating our equation for x equals 5 5 gives us 2 to the 5th power. Remembering that 2 to the 5th power means that we have 5 2's being multiplied together. When we multiply all those 2's, we find a final output of 32. Now let's evaluate the equation y equals 1 to the x for different values of x. Replacing x with -5 gives us 1 to the -5 power. The negative exponent tells us to move that expression to the denominator and raise that power to a positive after making that movement. 1 to the 5th power is 1 times 1 times 1 times 1 times 1, 5 1's being multiplied together, which gives us 1, and 1 over 1 simplifies to 1. Now let's evaluate this equation when x is 0. When we compute 1 to the 0, we apply the property of exponents that tells us that this is going to be 1. Now evaluate at 3. So replacing the x with the 3, we end up with 1 cubed, which is 1 times 1 times 1, or just 1. Example 3 gives us the equation y equals -3 to the x. Now, one comment here, there's a potential for an error. This exponent x is only attached to what's immediately before it. And what's immediately before this is a 3. The negative is sitting out in front. So it's wise for us to think of that negative separately as maybe a -1 being multiplied to that 3 to the x. So now let's try evaluating this equation for different values of x. So I'm going to keep this -1 in blue here. We're replacing the x with a -2. So we have our -1 being multiplied to 3 to the -2. The -2 power tells you to move that 3 to the denominator, making the exponent positive. We now have -1 over 3 squared, which is 9. Now let's try evaluating this equation for x equal to 0. So we have our -1 being multiplied to 3 to the 0 power. 3 to the 0 power is equal to 1. And -1 times 1 gives us -1. One final evaluation. Let's evaluate this equation where x equals 4. So we have -1 times 3 to the 4th power. 3 to the 4th power is 3 times 3 times 3 times 3. And after computing that product, we see that that is a -81. In example 4, our equation is y equals 0 to the x power. Evaluating this equation for x equal to -3 gives us y equals 0 to the -3 power. Applying the property of exponents to the negative power, we move the 0 to the other side of the fraction, making the power positive. But 0 cubed is 0, And so now we have 1 over 0, or 1 divided by 0, which does not exist. This is undefined. So the shortened version of does not exist is DNE, does not exist. Now let's evaluate this equation for x equal to 0. Recall, the property of exponents for a power of 0 tells us that if the base is 0, that this is undefined. So again, the answer for this particular computation is again does not exist. DNE. Now let's try x equal to 4. Replacing our x with a 4, we have 0 to the 4th power, which is simply 0. We now consider one final example in which our equation is y equals 5 to the negative x. So replacing our x with our negative 3 in our first row of our table gives us 5 raised to the positive 3, since the opposite of a negative is a positive. And 5 cubed is 5 times 5 times 5, giving us a final output of 125. Now let's evaluate when x equals 0. Replacing our x with a 0, we get 5 to the negative 0. But remember, negative 0 is just the same thing as 0, and 5 to the 0, according to our first property of exponents, is equal to 1. Now let's consider one final computation. Let's evaluate this equation at x equal to 1. So replacing our x with a 1, we have 5 to the negative 1 power. And the negative power tells us to move this 5 to the other side of the fraction and leave the power positive after that movement. So, in the end, we have a final output of 1/5. Evaluating exponential expressions advanced. We begin this video with two additional properties of exponents. The first property tells us that if we have 1 over a raised to a power m, that can be simplified as 1 over a to the m. So basically what's happening here is that this power of m is being applied to both the 1 and to the a. But 1 raised to any power is going to give us 1. So that is where the property comes from. So, as an illustration, consider 1/4 squared. Squaring the 1 gives us 1. Squaring the 4 gives us 16. So 1/4 quantity squared is equivalent to 1/16. Property 2 tells us that if we have 1 over a raised to a negative power m, that we can basically flip the 1 over a, making it its reciprocal, a over 1. Once you've made that flip, the exponent becomes positive. And again, you can apply that exponent to both the numerator and denominator But since 1 to the m is simply 1, and a to the m over 1 is just a to the m, we get a to the m. So as an illustration, consider 1/5 quantity to the negative 2 power. The negative exponent says flip the base. Once you've flipped, the power becomes positive. Squaring everything inside, we get 5 squared, or 25. In example 1, our equation is y equals 1/3 to the x power. Evaluating this equation for x equals -3, we have 1/3 to the -3 power. According to our second property of exponents on the previous slide, 1/3 to the -3rd power is the same as 3 to the 3rd. The 1/3 is changed to its reciprocal, 3 over 1, or just 3. And once we've made that change, the exponent becomes positive. 3 cubed is 3 times 3 times 3, which gives us 27 as our final output. Now let's evaluate at x equal to 0. We have 1/3 to the 0 power. But from a previous property of exponents, we know that this is equal to 1. Finally, let's evaluate this at 4. So we have 1/3 to the 4th power. Raising everything in this fraction to the 4th power, we have 1 to the 4th, which is just 1, over 3 to the 4th. 3 to the 4th is 3 times 3 times 3 times 3, resulting in a final output of 1 over 81. In example 2, our equation is y equals 1/4 to the -x power. Evaluating this equation for x equals -3, we have 1/4 to the opposite of -3 power. The opposite of -3 is a positive 3, and 1/4 to the 3rd power is 1 over 4 cubed. Remembering that 4 cubed means 4 times 4 times 4, we can write our final output as 1 over 64. Evaluating this equation for x equal to 0, we have 1/4 to the -0 power. But remember, 0 is just 0, so we really have just 1/4 to the 0 power, which we know is 1. Finally, evaluating this equation at 4, we have 1/4 to the -4 power, and the -4 power tells us that we can rewrite this expression as 4 to the +4 power. The negative exponent tells us to flip everything inside the parentheses, and after doing so, the exponent becomes positive. 4 to the 4th power is 4 times 4 times 4 times 4, which gives us 256. In example 3, our equation is y equals 2 to the 5 minus x power. Evaluating this equation for x equal to -1, we have y equals 2 to the 5 minus -1 power. 5 minus a negative 1 is the same thing as 5 plus 1. So we have 2 to the 6th power. And remembering that that means we have 6 factors of 2 being multiplied together, we see that our final output is 64. Now evaluating this equation, at 6 we have y equals 2 to the 5 minus 6 power. 5 minus 6 is a negative 1. 2 to the negative 1 power means that we have 1 over 2 to the first. The negative exponent tells us to move the 2 to the other side of the fraction, making the exponent positive. And 2 to the first is just 2, so our final output is 1/2. Finally, let's evaluate this equation at x equal to 7. So we have y equals 2 to the 5 minus 7. 5 minus 7 is a negative 2. 2 to the negative 2 is the same as 1 over 2 squared. The negative exponent tells us to move the base of 2 to the other side of the fraction, making the power positive after making that movement. 2 squared is 2 times 2, so our final output is 1/4.